Okay, so our motor is up and running. We have one coil wound on there so far. Just going to do some testing with that first. The first thing we're going to do in this video is I'm going to show you how much voltage is actually coming out of that coil now. It's only about 72 turns and the wire is 0.8 mil. I have the probe set on 10x. Also the scope is set on 10x. Now current meter, because everything here, all my equipment shares a common ground, our current meter is hooked to the negative side through the meter and into the motor. This is so I can put the ground of the scope on there as well without it affecting anything. So what I want to show you is just the voltage coming off of this coil, and although it won't kill you, it can give you a nasty tickle, even though we're going to be running on about 22 volts. It's going to be noisy. Now when I first put the motor together, I could not get it to work. I couldn't even get it to run without the diode across it, and I couldn't remember what exactly it was that I did to alleviate the problem before. I then remembered that I filed the brushes down to cover one segment of the armature each side only, not two. I then tipped the brushes a little bit to adjust the timing as well, and later on I'm going to make a couple of plates where I can slide the brushes around to different positions. But first up, we'll get it running, and I just want to show you the voltage coming off of that coil on the stator, because it is quite high, and like I said, it's going to be noisy because the brushes have been filed to a point. So you can clearly see our half wave AC. Let's see what I'll do. I'll turn that up the right way. That's better. And then I'll lift it back up. Okay, so you can see our half wave AC here quite clearly. That is going into the rotor itself, and you can see all the high voltage spikes when each rotor segment switches off. As you can see here, sometimes we're getting 300 volt spikes. Let's just lift it up one division. That's better. Okay, so that's what we have. That of course is without any load across our coil on the stator. So we'll turn that noisy thing off. So what we'll do now is we're going to grab our diode and a 1 ohm resistor, and I'll place the scope across the resistor, and I'll also hook channel A up across our current meter, and we will use the CSR in that to get a channel 1 scope trace on our scope. So we'll go ahead, set it up, and we'll come back to it. Okay, so all ready to go. All we'll have to do is hook this clip lead onto the other output end of the coil on our stator. Have our scope across the 1 ohm resistor and of course our diode. Now if you're doing this and you hook the diode across these two coils and the motor slows down, simply turn the diode around and you should get the correct effect. So we're going to put a 1 ohm load across that coil. I'll start up, let it build up speed first, and we'll have a look at our 2 meters. I have the other probe of the scope channel A, which is the yellow trace, across our meter here, current meter, so we can have a look at that as well. So that's across this meter here, it's showing our current. As you can see, the rectified AC, and also, just turn that back on, and also the very high voltage spikes we're getting when the brush is switched to the next segment on the armature. So that's our current draw and our current voltage. Voltage and current draw, sorry, not current voltage. So now we'll place our 1 ohm load across the coil. So our motor speeds up, we've got a 1 ohm load across it, and I haven't switched the probe back, which we'll have to do now. So, 2 volts per division on channel B, 500 millivolts per division on channel A. And you can still see the AC wave sign, or the rectified AC wave, which once again is upside down. And I'll leave it like that just to, actually no I won't. I'll switch it over. So it's messy, I'm not going to be able to stabilise it any more than that. As you can see, the AC waveform is the same frequency as our input, which is 100 Hz. As you'll see, our frequency is reading 3.16 kilohertz, and that's because it's reading each individual pulse from the ducted kickback when the brushes become open on the segment of the rotor. So there we have it, that's with our 1 ohm load across it. Peak to peak voltage of 4.6, 1.52 volts RMS. However, I doubt very much that the RMS value will be anywhere near correct with all those high voltage spikes going through there. There's our current draw now. So you can see our current's gone down with our 1 ohm load. And of course our motor sped up. What we're going to do now is I'm going to take this large cap here. I'm going to place this resistor, 1 ohm resistor, across the cap Then we're going to measure the voltage across the cap. It's 10,000 microfarad cap, 63 volts. Once we do that, we'll be able to get a voltage reading off of that, and of course it'll be volts over ohms, and from there we can work out exactly how much power we have coming out of that secondary coil, or the stator coil, which probably won't be very much, but not forgetting we also drop our input power to the motor down and increase the torque of the motor as well. So we'll go ahead and do that. Okay, so we've hooked it up to the big cap, and of course we have our scope across the cap, polarity correct. We'll be showing maximum voltage, minimum voltage, average voltage across that cap, and we'll also be able to see whether, let's have a look here, we'll also be able to see whether or not it has done a fairly good job at smoothing out the pulses, and this will give us a reasonably accurate power output of our coil. Still using the 1 ohm resistor, so it will be the voltage over 1 ohm. From that you will be able to calculate your power. So we'll make the noise again. Okay, so reasonably smooth. 1.24 volts. Our Vmax and Vmin is 1.2, and the average doesn't want to work. Change that. So that's not that that'll do anything, but anyway. So a reasonably clean line, which means we're getting a reasonable and accurate reading of our power output. And just have a second look. I'll chuck our multimeter across the cap as well. If we can get it on there. It's a bit crowded here. Okay, 1.2, 1.16, saying about 1.14. So extremely close. And then of course we have current going into it. But as you can see, it's not very hard at all to get a very close to exact output reading from any kind of pulse system that's using high voltage inductive kickback spikes to charge a battery. You simply do a setup like this and put your cap in between your output coil and your scope. Nice big smoothing cap, not hard to do. And of course you can do the same on the input, and that is one way to get an accurate reading of power in and power out on any pulse system, providing your cap's big enough. And as we could see by the scope, done a pretty good job at smoothing out the spikes, so as we could take an accurate reading. 1.6 volts over 1 ohm, what's that, about 1.4, 1.5 watts, something like that. But anyway, not very much, but as you can see it drops our power input down, speeds our motor up, and of course will give the motor more torque, and these really aren't a good motor. to be doing this with. We could build far better than that, but that's what we have. And of course we are only using one coil still. I guess the next job is to get the second coil on and see if we can gain as much again, drop some more current on the input, and gain some more power on the output of the shaft. So see how we go with that.